Hello students, this is our physics class and we are dealing with the topic optics. In the previous session we have already discussed about the concept of reflection by mirror, types of mirror, and the image formed by both the types of mirror, that is image formed by concave mirror as well as image formed by convex mirror. So in the image formation we have discussed about different types of images for different object distances, the nature of image for different types of object distances or different object distances. So while discussing the image formation diagram, I have mentioned that for image formation diagram, while drawing, you have to take the distance, radius of curvature as well as the focal length. The focal length you have to take half of the radius of curvature, or the radius of curvature you have to take the double of the focal length. So in the second part I have mentioned this point. For time being you have to take radius of curvature, you have to take double the focal length for drawing purpose. In the next session we shall study how that relation is. So in this third part we are going to see how the radius of curvature and focal length are related. So today we shall study the relation between focal length and radius of curvature. For that, you have to consider a concave mirror. This is also true for the convex mirror also, but we are considering, for our convenience, we are considering the concave mirror. We are considering a concave mirror, and we are considering object at infinity. Object at infinity means the rays emitting from the object will be parallel to the principal axis. So we are considering an incident ray. Only one ray we are considering, incident ray AB, which is parallel to the principal axis. Incident ray AB which is parallel to the principal axis. Now again, according to the definition of principal focus, when the parallel ray is incident on the concave mirror or convex mirror, when the parallel ray is incident on the mirror, it passes, after reflection it passes through the principal focus. So AB is the incident ray. After reflection, BF, it passes through the principal focus. So BF is the reflected ray which passes through the principal focus. Now to measure incident angle and reflected angle, normal should be there, because always we measure with respect to normal. Angle made by incident ray with the normal is called as angle of incidence, and angle made by reflected ray with the normal is called as angle of reflection. So for this purpose we require normal to the surface. Now what is normal to the surface? It is a perpendicular line drawn at the point of incidence. Perpendicular line drawn at the point of incidence. So at point B we have to draw a perpendicular line. Now what is this point B? Again, remember the portion discussed in the second part, how the spherical mirrors are formed. Spherical mirrors are formed by a sphere. They are part of a sphere. Now according to that concept, point B is also a point on the sphere. So always any point on the sphere to the center, any point on the sphere to the center, this line joining is called as radius, and radius is always perpendicular to any point on the sphere. So if you join a point B to the center, this line becomes perpendicular to the point B, and the distance between the principal focus and pole is focal length. The distance between center of curvature and pole is radius of curvature. So BC is the normal that we are drawing at the point of incidence. So this is all about the ray diagram. Now we can measure the angle of incidence. It is nothing but angle between the incident ray and normal to the surface. So this we take as I, and angle between reflected ray and normal to the surface. This is angle of reflection R. Now again, remember the laws of reflection. Remember the laws of reflection. In that, the first law is angle of incidence is equal to angle of reflection. I is equal to R. So from that, we can write angle ABC, angle ABC and angle CBF. Both are equal. I is equal to R. So instead of writing I is equal to R, to both the angles we use some common notation, that is equal to theta. Angle I is equal to R, which both are equal to theta. Now, this is the first equation. The second one we can take is angle ABC, angle ABC and BCP, angle ABC and BCP. Look at their position, they are alternate to each other. So again you can take angle ABC is equal to BCP. Now I we have taken equal to theta. I we have taken equal to theta. So according to that, ABC will be equal to BCP, which is again equal to theta. Now coming to the third equation, ABF. ABF. This complete angle ABF means which includes I as well as R. So theta and theta. So ABF is equal to 2 theta, which is equal to BFP, which is equal to BFP. Again it is 2 theta. So our angle BFP becomes 2 theta. So these three equations we have. Now this line BP for small angles, or the paraxial rays very close to principal axis. For the explanation purpose we have taken this enlarged diagram, but if the AB paraxial ray is very close to principal axis, then BP is taken as perpendicular to CP. BP is taken as perpendicular to CP. So if we take BP as perpendicular to CP, then triangle BFP as well as triangle BCP both becomes right angle triangles. Again, for small angles, in the first year you all have studied small angle approximation. For very small angles, tan theta is nearly equal to theta. Tan theta will be nearly equal to theta. Now using these two assumptions, BP is perpendicular to principal axis as well as tan theta is equal to nearly equal to theta, we shall move on to the next part, that is, so as I have mentioned, BP, if you take perpendicular, then BPC becomes a right angle triangle. So for a right angle triangle you can apply the trigonometric functions. So in the triangle BPC, the angle theta you have to apply the tan function. So tan theta, as well as it is a small angle approximation, tan theta will be equal to theta. So what is the tan theta equation you can write? It is opposite upon base, BP upon CP, BP upon CP. So tan theta is nearly equal to theta, which is equal to BP upon CP. Let us denote this as equation 1. Then another right angle triangle that you are getting is BFP. A small mistake over here. It should be BFP. So in a right angle triangle BFP, angle is 2 theta, for which you have to apply the trigonometric function tan. So tan 2 theta is nearly equal to 2 theta. So what is the equation? Opposite upon base BP by FP. Now let us denote this as equation 2. Now the theta value from equation 1, substitute the value of theta in equation 2 from equation 1. So theta value is BP by CP, that you have to substitute here in this theta. So it becomes 2 into BP by CP is equal to BP by FP. So 2 into BP by CP is equal to BP by FP. BP get cancels. So the equation remains is 2 1 upon Cp is equal to 1 upon Fp. Now substitute the values of Cp and Fp. Cp means from center of curvature to the pole. Fp means from principal focus to the pole. So from center of curvature to the pole is nothing but radius. From principal focus to pole is nothing but focal length. Substituting the value 2, 1 upon r, Cp is r, 1 upon r is equal to 1 upon f. Now cross multiply, you are going to get 2f is equal to r, or f is equal to r by 2. So this is the relation between the focal length and radius of curvature. Radius of curvature is always double the focal length, or focal length is always half of the radius of curvature. This relation is true for convex mirror also, even though we have derived this relation by using concave mirror. This holds good for convex mirror also. So this is the reason why I have mentioned for image formation diagrams you have to take the focal length almost half of the radius of curvature, so that you can get the correct image formation patterns. So the next we'll move on to the mirror equation. So this equation, this derivation gives you the relation between focal length and radius of curvature. In the next part, that is mirror equation, this equation, the derivation of this equation gives you the relation between object distance, image distance and focal length. So for that we have to consider a concave mirror. Consider a concave mirror, and whenever you are deriving any equation, you have to derive the equation with the help of a diagram. Some students by heart the diagram and position of the rays. Don't do that. Understand the image formation, and then accordingly you have to draw. So here we have taken a mirror, where after drawing the mirror, the first point you have to do is you have to draw a principal axis. You have to draw a principal axis at the center of the mirror. After drawing the principal axis, you have to mark the pole of the mirror. After marking the pole of the mirror, you have to mark the principal focus and center of curvature. See, look at the position of the principal focus and center of curvature. So here is our principal focus and the center of curvature. Look at the position. Your C is double the length of the PF, double the length of the principal focus. And here we are taking an object AB which is beyond C. Object AB beyond C. When the object is beyond C, where the image should be formed? Between C and F. For image formation, we have to take the rays. So first ray always we used to take is parallel to the principal axis. So we are considering the first ray AM parallel to the principal axis. So any ray parallel to the principal axis after reflection passes through the principal focus. Yes, after reflection passes through principal focus. So AM is our angle incident ray. MFD. MFD is our first reflected ray passing through the principal focus. The second ray that we can take is the ray passing through the center of curvature retraces its path. The ray passing through the center of curvature retraces, it hits the mirror and retraces its path. Now these two reflected rays MD and NC are meeting at some point. So that point is corresponding to, that point is the image point corresponding to the point A. So that we can draw as A dash. So only for image formation these two rays are sufficient, but for calculation purpose, for derivation purpose, we require one more ray. So where that ray we are going to take is from A to the pole, from A to the pole. And how the reflected ray is going to be? The reflected ray, it is following the laws of reflection. Angle I is equal to angle R. So at what angle it is incident? At the same angle with the principal axis, which is nothing but the normal to the point of incidence. At the same angle it is going to reflect with the angle R, and this reflected ray is also going to pass through A dash. So all these three rays are meeting at point A dash, which gives the image of the A point A. So we can draw the image A dash B dash, A dash B dash. So coming to the derivation. Here AB is the object, AB is the object, A dash B dash is the image. Now for paraxial rays, again we have to approximate here. For paraxial rays, paraxial means very close to the principal axis, very close to the principal axis. AM we are taking very close to the principal axis. If it is very close to the principal axis, then look at this distance, very small. So for a small distance, if we take a larger distance, it appears to be curved. But if you take a small distance, it appears almost straight line. So for paraxial rays approximation we are taking, for paraxial rays, MP can be considered to be a straight line, which is perpendicular to CP, which is perpendicular to the principal axis. Then the two triangles A dash B dash F, two triangles A dash B dash F, A dash B dash F is a small triangle that we are taking, A dash B dash F, a right angle triangle, and MPF. See, this is the straight line, almost straight line we are considering, so this becomes a perpendicular, MPF. So in these two triangles, two angles are equal. This is a right angle triangle, this is a right angle triangle. Angle P and angle B are right angle triangles. angle F, and here also angle F. Opposite angles, they are same. So if two angles are same, you can consider the two triangles are similar triangles. Two triangles are similar triangles, then you can have the ratio of their sides should be equal. So you can write B dash A dash, B dash A dash is equal to PM. B dash A dash is equal to PM. Another side that you can take the ratio is B dash F and PF. B dash F and PF. You may ask, another side is also there, that is MF and A dash F. That also can we take MF A dash F and MF. You may ask, this is also possible. Why we are not taking this? Only these two sides we are taking. Why we are not taking means for B dash F. For B dash F, we have the substitution. For PF, we have the substitution our focal length. For PM, we have a substitution for AB as a object height. But for MF and A dash F, we don't have any substitution. So it leads to the complication. So such points we avoid. So that is what the reason we are not taking this side for equating for the ratio. So here B dash A dash upon PM is there. Now PM will be equal to BA, because these two rays are parallel to each other. Parallel to each other means the other sides should be, the perpendicular distances should be same. So in place of PM we are substituting BA. So B dash, the equation becomes B dash A dash, B dash A dash upon BA will be equal to B dash F upon FP. This we are taking as equation 1. Then next triangles we are taking is APB, APB, APB and A dash PB, A dash PB. So how we are taking as a similar angles? Two angles should be same. If we want to take the two triangles similar, among in those two triangles, two angles should be same. So here two angles are, angle B is right angle triangle, angle B dash is a right angle triangle, and in this triangle APB, this is equal to I. A dash P B dash, this is equal to R. Now from laws of reflection, I is equal to R. So in both the triangles, this angle and this angle both are same. So in both of the triangles we have two angles same, two angles same. So we can take these two triangles as similar, these two triangles as similar. So A dash B dash P and ABP are also similar. So if we have taken both the triangles as similar, then you can have the ratios of their sides equal. Now we can write B dash B dash A dash equal to BA. B dash A dash, B dash A dash equal to BA. Then B dash P, B dash P, this is the base of the first triangle. B dash P, the base of the another triangle is BP. B dash P, BP. So this we can take as equation 2. Now comparing equation 1 and 2. Comparing equation 1 and 2. Look at their LHS and RHS. So both the equations, LHS side is B dash A dash by BA, B dash A dash by BA. So you can equate the RHS right hand side of both the equations. You can equate right hand sides of both the equations, that is B dash F by FP will be equal to B dash P by BP. B dash F by FP is equal to B dash P by BP. Now B dash F, you don't have any substitution for neither the object distance nor the image distance. So what will do? B dash F, B dash F, B dash F can be written as B PB dash minus FP. PB dash minus FP gives you B dash F. B dash P minus FP. B dash P, B dash F can be written as B dash P minus FP. The remaining things as it is same. FP is equal to B dash P by BP. Now applying the sign convention. For these values we have to apply the sign convention. Now B dash P. B dash is the point where image is formed. P is the pole of the mirror. Now according to the sign convention, the distances are always measured from the pole. Then it becomes PB dash, and the distances are taken positive if the measurement is along the direction of incident ray. If it is opposite to the direction of incident ray, the measurement has to be taken negative. PB dash, PB dash. See, PB dash is in this direction. From the pole you have to measure the distances. PB dash, but our incident direction is opposite to the PB dash. So PB dash we have to take as a negative. PB dash we have to take as a negative. From the pole to the image, the distance is image distance V. So B dash P becomes minus V. FP, FP from the principal focus to the pole, from the principal focus to the pole. So we have to measure from the pole to principal axis. From the pole to principal axis, look at the direction of the measurement. Again it is opposite to the direction of the incident ray. So PF is focal length F, but as we are measuring it opposite to the incident ray, it becomes negative. Then BP, BP from the object to the pole. From the object to the pole is the object distance. From the object to the pole is object distance U. But how we have to measure? According to the sign convention. From the pole to the object. From the pole to the object. So this is our direction of measurement. Again it is opposite to the direction of the incident ray. We have to take that as negative. So minus U. Now with these values, with the sign convention, substitute these all in the equation 3. So B dash P is minus V, minus of minus F. FP is minus. So minus of minus. So here we are getting minus V, minus of minus F upon FP is minus F, minus is equal to BP is B dash P is minus V upon minus U. So minus of minus becomes plus. So it becomes, the equation becomes minus V plus F divided by minus F is equal to minus V by minus U. Again this minus get cancels. So what you are going to get is minus V plus F divided by minus F is equal to V by U. V by U. cross multiply. When you cross multiply, this becomes minus Vu or otherwise we can take with the minus sign only. We can go with the minus sign only. So when you cross multiply, this minus get multiplied with the other side. So minus V into minus U plus F into minus U. The other side cross multiplication is equal to minus F into minus V, minus F into minus V. So it becomes UV minus UF is equal to VF, is equal to VF. Now divide the whole equation by UVF. Divide the whole equation by UVF. So you are going to get UV divided by UVF minus UF divided by UVF is equal to VF divided by UVF. So UV get cancels here. What remains? 1 upon F minus UF get cancels, remains 1 upon V is equal to VF get cancels, remains 1 upon U. Remains 1 upon U. Now this equation you can rewrite as 1 upon F minus 1 upon V. If you take it on the other side, it becomes plus 1 upon V. So 1 upon F is equal to 1 upon U plus 1 upon V. So this is the relation between focal length, object distance and the image distance. This equation is called as mirror equation, which relates to focal length, object distance and image distances. You may ask, why only these two triangles we can take? Another triangle that you can consider is A dash B dash C, A dash B dash C and ABC. These two triangles also you can consider as a similar triangles. So first one ABF and MPF. These two triangles we can consider. The another two triangles that we can consider for similar are these two triangles. So take it as a homework and work out it. Take it as a homework and work out for these two set of triangles as similar to get the same result. You are going to get the same result. So here instead of image distance, you are going to get it in terms of center of curvature. Directly the R value you are going to get, where you have to substitute R is equal to 2F. R is equal to 2F. So practice the equation, and if you want, try with the other triangle, or else practice with the given equation. Now in the previous sessions, while discussing the image formation, we have seen that if here is our F, here is our C. If the object is between C and F, how we draw the image formation? First line we have to take is parallel to the principal axis, which passes through the F after reflection. The second ray we are taking passing through the principal focus, after reflection becomes parallel to the principal axis. So wherever those two rays meet is our image formation point. So here is the image that we are going to get. So look at the image size. It is bit enlarged compared to the object. So you can say image is enlarged. By what quantity it has enlarged? Whether it has doubled the size of the object or 1.5 times, 1.2 times, 1.3 times, whatever it is. How to find the enlargement that has occurred in the image? For that, you have a magnification equation. So magnification for linear magnification. Linear magnification means enlargement in the size of the image, magnification. So it is defined as the linear magnification. The magnification is defined as the ratio of size or height, anyone you can take. It is defined as the ratio of the size or height of the image to the size or height of the object. It is denoted by a letter M. So you can consider again the same first two triangles A dash B dash P A B P. A dash B dash P and A B P. These two triangles A dash B dash P and A B P. The same equation we are taking. B dash P upon BP. So A dash B dash by AB. A dash B dash is the height of the image. With the sign convention we are substituting. So here is AB, A dash B dash. So A dash B dash, look at the A dash B dash. It is below the principal axis. So heights measured below the principal axis are taken negative. So H dash is the height of the image. By sign convention it is minus H dash. AB is equal to H, height of the object, as it is above the principal axis, it is H. So H dash minus H dash by H is equal to H is equal to minus H dash by H is equal to B dash P is our principal focus. Principal focus. So B dash P is from image to the pole is image distance. BP from uh, from object to the pole, is the object distance. By sign convention, as we are measuring from the pole to the object, from the pole to the image, both are opposite to the direction of the incident ray. Both we have to take negative. So minus V by minus U. Minus get cancels. We are getting minus H dash by H is equal to V by U. Minus H dash by H is equal to V by U. By definition, H dash by H, the ratio of image height to the object height is equal to M. Image height to the object height is equal to M. So H dash by H becomes M. V by U. Minus M is equal to V by U. So minus sign, we shift it on the other side. It becomes M is equal to minus V by U. M is equal to minus V by U. So the magnification, by what quantity the image has magnified, by what quantity the image has magnified, that you can get by getting the ratio of image distance to the object distance. If this ratio is equal to 1, then you can understand that magnification has not taken place. Object and image are of the same size. If the ratio is more than 1, it indicates the image has been magnified. If the ratio is less than 1, it is understood that image has been diminished. So this is our today's discussion, where we have discussed the relation between F and R and the mirror equation, and also the linear magnification. So go through the video again and again and try to understand the concept.